In the last video, we took a look at this definition, this rigorous definition for what exactly a limit is, and it had to do a lot with these red and blue intervals. Now, what we're going to see here is that working with these particular intervals will be a bit complicated in this current interval notation form. And so it's going to be important that we go ahead and use an idea associated with the skills check to help try to rewrite this particular definition. Take a look down here at the note. Determine an interval that is going to be communicated by each of the following absolute value inequalities. Now let's pretend here that the value a and the value delta are just numbers, and I'm going to try to solve for x. You might recall how it is that we do this. We can think about the inside of this thing that I have here, and when inside the absolute value bars, and if I want that to be less than delta when absolute valued, that would mean that I need that inside amount to actually be either smaller than delta already, or at least bigger than negative delta. This is again exactly what we did on the skills check. Now I can easily see that I could solve for the value of x by simply writing that I am going to add a to each side here. So I'm going to add a to delta, and here I'll add a to negative delta, or I'll have a minus delta. So notice that this then communicates an interval that is a minus delta to a plus delta. And if you take a look even at what I have at the very top of the screen, you'll realize that this is the same red interval that we were talking about at the end of the last video. So this absolute value inequality is the same thing as saying that x is in the red interval. That's kind of a cool idea. Now if you take a look down here at the next one, you can see that we can do the same sort of thing. This time I'm going to treat f of x like it's the thing I want to solve for. And so again, I'll start by thinking about what's true about this inner piece of the absolute value. If I want all of this to come out less than epsilon, I would need to have the whole inside be less than epsilon already, or maybe be bigger than negative epsilon. So when I go ahead and I now write this in, and I try to get f of x all by itself, that's going to give me f of x minus epsilon. Oops, sorry. Not f of x, that's not the one I'm moving. I'm going to move L minus epsilon, and then over here, L plus epsilon, which of course, if I wrote in an interval notation, I would see that f of x now is falling inside the interval of L minus epsilon to L plus epsilon. So I can see here again that the blue interval that I had in the definition up above is actually the same thing, or is being communicated right here by this absolute value inequality. So we're going to use this knowledge to kind of update the previous definition to see how we could possibly kind of restate it. So let's see what we have. Let f be a function defined on an open interval that contains a. Then we will say that the limit of f of x as x approaches a is L, that is, we could state this if the following holds. We would say for every number epsilon that's greater than 0, there is a number delta greater than 0, such that if x is inside this red interval, then f of x will be inside the blue interval. But I can write that now by just using this these two absolute value inequalities. So we can say if absolute value of x minus a is less than delta, then absolute value of f of x minus L will be less than epsilon. And so again, we've communicated if x is inside the red interval, then f of x will be inside the blue interval. So the reason that we want to update the definition with this is that using absolute value inequalities is actually going to make it easier to evaluate the limit, because we'll actually have some inequalities and almost like pseudo equations to try to work with to help try to figure out for what values of x this will actually be true.